All right, good evening, everyone. Welcome back. Welcome to episode 5375 of Tech Talk. No, actually not, but it is a bit of a of a special number. This is episode 10. So this is the 10th. This is the 10th time. This is episode 10 of Tech Talk Thursday. And as always, I hope everyone is having a wonderful morning, day, afternoon, evening, night, wherever you are around the globe, or whatever your sleep schedule is. And hello and good evening, as always, to PX Slip, and thanks for joining me. So, a couple of and of course, a big welcome, obviously, other than the folks on Twitch, obviously, watching live, and if you're on YouTube, appreciate your checking out the VOD, and if you let's see, if you're on Twitch, please hit the follow button. If you're on YouTube, hit the subscribe button. Since I'm
that's not confusing at all.
This is not confusing at all. The only good news is, since I'm not a Twitch anything or other, there is no subscribe button on Twitch, and there's no join button on YouTube. So whatever button you find down there, just click it. And we would appreciate it. Speaking of YouTube, we're not totally set up yet, but we're making huge progress. So check out the link below. A lot of our back issues are on YouTube, and more are coming. Couple other notes. So I think most of you know that I'm a retired IT professor at Ohio University, and as of 2 days ago, I agreed to teach a class at Ohio University, which is going to be fun. That's something I wanted to do. There were some administrative hurdles that it wasn't clear for a little bit as to whether those we would able to overcome those or not. So if they have been overcome, and I think my colleagues in the McClure School who made that happen. So starting next week, I will teach a class on that originally was a class that is called Voice over IP. And part of the reason why I was asked to do that is to update that class to really, broaden it out. Obviously, the biggest thing is to voice and video over IP, and we're gonna spend a lot of more time on things like things like Teams and Twitch and the Zoom and those kinds of things. So that's gonna be good fun, and so kind of necessity, Tech Talk Thursdays will, at least for a little while, and they did, some of them in the past already have already done that, but Tech Talk Thursdays for a little while will, off my necessity, kind of touch on topics that are relevant for me in that class anyway. So if you're curious as to how, I've always envied my colleagues in the English department. Most of the people they teach about, most of the authors are dead. And even the ones that aren't dead, once they publish a book, they usually don't change it. I'm teaching in a field where whatever was relevant 6 months ago, forget it. It's old news. Yeah. So if you're wondering how someone in the IT field gets ready for a class like this, you've already seen some of it, because in fact behind the scenes, some of what you saw on the previous Tech Talk Thursdays were kind of motivated by the fact that I wanted to learn stuff that was relevant for this class even before I knew I was going to teach it. So here we are. The topics will be somewhat driven by things that I'm kind of interested in as I take the students through sort of an exploration of, mostly from the networking perspective, of how this stuff actually works. That does not mean that we're not paying attention to local streaming tool. And by the way, just as a and I don't know if he's going to show up as he was still Old Depressed Gamer was still streaming when we went on. He was chasing aliens in Elite Dangerous. But if he shows up, it'll be great. But in any case, let's do a shout out for ODG, because local streaming tool, of course, is something that PXLip and I kind of got interested in after talking to him a bit about things that he does. His setup, OBS setup for Twitch stream is completely customized. And so, we that's where PXLip and I kind of got to talking about how do we do that in a much more modern way than just, basically hand coding CSS and HTML. So that's where the idea came from. Some of the original concepts came from. So LST is very much still a thing. Interestingly enough, ODG is actually building a very different version of a basically an updated version of his overlay. They're going to be very different, taking very different approaches, but it's fun, and I think hopefully we're going to be able to interact with him going forward.
So it'll be a fun opportunity to sort of compare and contrast our approaches.
Yeah, the main difference being that he's using a database as an intermediary. He's doing sort of a pub sub. A local pub sub environment.
Doing like a message queue, probably.
Yeah, setting up. He's using a database as a message queue, which is going to be kind of a fun thing to watch. So the reason I mention all of this is we are going to kind of not restructure, but we want to do order things a little bit differently. So for the next few weeks. And and again, starting today, and so in a couple minutes, we're going to start with PXLip sort of giving us an update on where we're at with LST. Sometimes we might spend a bit more time on, especially this code to show or a demo or something like that. Occasionally, he will stream the actual development on his channel, and I'll shout that out when that happens.
Eventually, I'll get back into that. It's been bad recently.
Contrary to me, he's actually gainfully employed, so he doesn't always have time to mess with that. So you'll kind of have a sense of where that's going. We'll post stuff on the website, and we're hoping to. Hoping that kind of slowly but surely this will keep developing. And if interesting things like the whole OAuth stuff that we talked about a couple of streams ago, of course, was very much driven by the fact that we needed all that to work to make the local streaming tool a reality, and we needed that. Very much needed to have OAuth capability. So if other sort of interesting topics like that pop up, we'll definitely spend a stream to go over those. So with that, do you want to give us a snapshot of where we're at with it now?
Yeah, actually, I can be super fast. There's not been a lot of updates. Still coming out of the holiday fugue. too many cookies and too much eggnog. Well, we did get OAuth up and running, which was obviously a big deal. Which should make future interactions with other platforms much easier now that we've got one working. So I think the first thing that I'm going to be tackling, hopefully in the coming week, I've got a number of days off of work coming up, just the layout of some holidays. I took some extra time, and I'll have a couple of days. So the plan is to start with the simple, start with the chat commands, get the bot listening to a given chat channel and reacting to commands, and then we wire it up to OBS.
Okay, so yeah, so we have OAuth. That means we can hook into Twitch, which is what we need for chat. And so the next big thing then will be WebSockets, really, to talk to OBS.
A WebSocket connection to OBS, right? Because we'll be doing WebSockets to talk to Twitch chat. Twitch chat is run over WebSockets, kind of. It's a weird conversation there, but so we'll be setting up a WebSocket client for Twitch chat, and then a WebSocket client as well, actually, on to talk to a different client to talk to OBS via OBS WebSockets.
Oh, OBS is a WebSocket listener built in, doesn't it?
Yeah, well, not built in. It's a plugin.
Oh, it's a plugin. Okay.
Yeah,
but
so
you can configure to listen on a WebSocket.
Yes, it's literally called OBS WebSockets. It just basically exposes a WebSocket server with a number of events you can fire or channels that you can wire into to either listen for events that OBS outputs or trigger events on OBS that cause different things
Cool.
to happen.
Cool. All right, so don't let me forget then, as we do planning. I think either a week from now or 2 weeks from now, let's do a stream on WebSockets. I meant to do that
Yeah.
anyway, and WebRTC is WebSocket based, so that fits in perfectly well.
No, that sounds great.
With the kinds of things that I'm doing. So it's, and you know, as we've done before. I mean, I think what I would love to have kind of a really super simple demo. Where we just have
we'll put something together.
Where we just have a really simple point-to-point connection, basically, so we can actually see what's going on. Let's see. Right. Anything else on LST for now?
No, not at the moment. That's all that's happened so far. So hopefully, as the new year starts getting into things, I'll actually have more interesting stuff to present and more interesting stuff being shown on stream at some point.
Cool. Yeah, OAuth is a big one, right? Just to, if folks hadn't joined us before, OAuth 2. And actually, you said you went with OpenID Connect, actually, right?
Yes, which is basically just OAuth with
we're
a couple of extra pieces hooked into it.
Right. So we're getting the the user profile and some user information out of the system.
It basically, that's exactly it. It basically just gives me some basic information about the user who initiated the OAuth request, just so I don't have to go out and ask for it later.
You just triggered that echo we had last week. I don't know what you did.
I don't know what I did either.
You were fine until just a minute ago. It's not bad. It's just you sound like Resurrection Firm. The reverb turned up.
I say, is it?
That's much better. Yeah, now? It's gone now.
Okay. Apparently, I can't turn on one of my other Chrome profiles.
Oh.
I was opening a Chrome window. It could be something else, but that was the particular thing that you called out. So
interesting.
Yeah, I'm confused by that one.
Yeah, we'll figure that one out. There's another stream coming.
Yeah.
This stuff can get kind of interesting and weird at times. So anyway, we'll talk about OAuth 2 and Open Connect. At this point, pretty much every service that we will want to tie into our streaming infrastructure for whatever purpose is going to use OAuth to authenticate, so that your ability to actually access the service on some user's behalf. And so as PXLab said, we went through we went through the demo code and we went through the standard. But getting this actually working correctly in an application is never quite as simple as it sounds in the standard or the demos.
It really never is.
So having that running is big, because it gives us the it puts us in a position to expand this out to other servers, and most importantly, obviously, it puts us in a position to talk to Twitch.
Yeah, for me, I've wrapped my head around it once. Doing it a second time or a third time in the future is going to be relatively straightforward.
It's just one of those things where there's like an ambiguity. There are always ambiguities in standards, so sometimes just wording that isn't very clear. And so you try to implement something even with a library that you have the same sort of disconnect of what exactly do you expect me to do here? All right. So both from the perspective of we've been talking about streaming and streaming tools and whatever, and of course from the perspective of this class I'm going to teach. I thought one of the things that might be fun to look at today is just codecs and audiovisual AV containers, part of it I kind of got really interested in doing this because I spent several hours on ODG Old Depressed Gamer stream a few weeks back, and he was playing with OBS Ninja, the site that we talked about early in this series. And I was helping him sort of debugging things, and there are settings in OBS Ninja and in many other configurations like OBS itself that I personally just couldn't I wasn't sure what they meant. I really didn't have a good sense of how this sort of audio encoding, the media encoding works, and how the different settings that you have access to actually work together. I'm not claiming I know much more, but I can explain what I know, which is a starting point. And that's, of course, also what I'm going to do in my class, is just to start poking at enough of it so that from a perspective of managing a network and figuring out what a network has to do, or figuring out if I want to, especially with Twitch streaming, and if I want to target a certain level of quality, what do I need to do to make that happen? And how does it relate to things like bit rates? But very early on we did we looked at jitter, and we looked at just sort of raw speed across the network, and so if I can carve out some of it for the stream, how does that relate to quality? And it turns out to be fairly complicated, and I was still digging my way through that. So one of the things that I want to acknowledge, let me get this in the right place, and I'm going to need my drawing pen here in a second. But one of the things I wanted to acknowledge was fortunately, one of my colleagues is an expert especially in game audio, game and VR audio production. He has an MFA in film. As one of my colleagues at the McClure School, and I asked him about video encoding, and asked him about what on audio and audio encoding. Where do I go to get some decent information? This is the book that what you see up on screen. This is the book he recommended, and I really like it. It is quite good. And so I've been reading this, and a lot of what I'm talking about today is sort of partially comes out of that, and then other places. Some of it already knew, which is this gave me some ideas, and both today and in the future, I'm going to point out some of the tools that he lists in that book that I found very interesting. There's one I don't know the name of. It's not something we're going to look at today, which is why I didn't bother to remember to write it down. So we talked, I guess was it the last stream, about Wireshark and getting Wireshark to decode TLS encrypted streams. And so one of the things that the author of this book tracked down is a web proxy that you can run that is specifically designed to help you debug and determine video quality. So you basically like I'm streaming now. I have OBS running, and I'm sending a video stream to Twitch, which recodes and sends it out to those of you that are on Twitch, and I'm also locally recording the video and audio that we're producing here, so there's a web proxy tool that would allow me to take my stream, send it through this web proxy, and basically get basic information about the stream. I could connect to the stream from somewhere. From another machine that goes through this web proxy. I could limit the bandwidth and then look and see how the quality behaves, and look at all the details of the stream that are going on, much like we were doing in Wireshark, but it's in a different tool that is very much designed to to do this. So I'm sure I'm going to play around with that in a future stream. But I found this super interesting, and it's just one of several things that I learned in this book. So the so I want to try and talk about a couple of different aspects of taking audio and video, which is what we're doing now, and there's this kind of a separate topic, one I'm not going to get to today, that has to do with things like when I share PXLib's screen. That's another type of data, right? And in some ways it's a bit easier. So generally, multimedia streams, AV streams in things like Teams, Zoom, WebEx, WebRTC, OBS Ninja, tend to recognize one or more audio stream, one or more video stream, and one or more sort of data streams for sharing screens or exchanging files or doing those kinds of things. So what can get a lot of these things can get confusing just because of terminology, and so let's get just a regular pen here. So let's think about mainly audio right now, just because it's easier, right? So I'm talking right now into a microphone that's attached to my headset, and this is an analog headset. Is yours is analog as well, right? It's a regular
It's analog to USB.
Okay, so basically what I'm saying is we each of us have a microphone. Let's see. I can't draw today. Usually a little bit better at this. So let's do this. So I've got this boom microphone coming from my headset, and it's wired into my computer. The audio signal on this wire is an analog signal, just an electrical representation of my voice. And I'll have an app we can look at in just a second, and we'll see what that looks like. So that's kind of important because in most voice applications, that's how we start. We start with something that captures audio. In most cases, not always, but in cases where we're talking about like a human voice or like an instrument performance or something being captured. Generally, we start out with an analog electrical replica of the sound, like my voice in this case. And so once I get to the computer, so this is analog. Once I get to the computer, I want to send this out somewhere. The first thing I would do is I have to make this digital, and that's the job of a codec, which is short for coder decoder. So pretty much somewhere on the sound chip on the motherboard of my computer is an analog to digital converter that takes care of this. If my headset was a USB headset, that analog to digital converter would be built into the headset to produce a digital signal, because USB is a digital signal. All right, so that's a codec, and there are many of them. That begs a question. I have absolutely no idea what the A to D chips on the motherboard actually do. I'm not sure what the internal audio is. That's would be kind of fun to look up. I don't
Yeah.
even know where to start looking for that. But I might just look that up at some point. Um, and I'm not even sure. I think USB would have its own. I think USB may have its own definition. I'm not sure for USB audio. But the point is there are many codecs available, and you can pick an appropriate one that's appropriate for your purposes. That's one half of the battle. And so so you pick a codec, and that influences essentially how the voice signal is stored as a stream of digitally encoded numbers. That in and of itself is sufficient to handle stuff flowing around inside the computer. Right, so if I tell Windows, hey, go to that chip and pick up audio, that's all internal to the operating system. So as long as everybody agrees what the encoding is, that should work. I don't know what it is. Never actually thought about it until this minute. And I can change. So once I have an audio signal in this sort of environment, I can then basically recompute it and then store it in a different format if I needed to. The codec itself defines what the numbers mean. They define when I have a series of numbers, how does that relate to the original analog voice or music or sound signal? But that's it. That in and of itself isn't quite enough to actually transmit it either as a file or a stream. To actually transmit this out on the wire, I need to also define something called a container. And generally, we tend to talk about file formats sort of at a casual level by mentioning the container name. So MP3, MP4, QuickTime, MOV files are container formats, not codecs. In fact, many containers can carry multiple formats. So I can choose what type of what codec to put in there. So I can choose a container, I can choose a codec somewhat independently. Not every container can carry every codec, and obviously not. It depends very much on who the recipient is. Web browsers have a certain list of containers and codecs they support. The mobile phones have certain a list of containers and codecs they support. Apple has its ideas. The Android phones have their ideas to what they what they support.
Yeah, I'd say it gets particularly fun when you start talking about web browsers.
Right.
The support matrix is really pretty weird.
Yep.
Because Firefox is unable to use H.264. I want to say I could be getting that flipped, but one of them because it's burdened by a patent.
So, yeah, that's a really good point. So the list of codecs. One of the things that distinguishes the list of codecs is whether or not, and I think the terminology they use is whether or not the codec is, or the container is encumbered.
That's it. Sorry, I misused that word. Yes, encumbered is what I've seen as well.
And an encumbered codec or container format means it has usually a patent and a license agreement attached to it. Yep. The reason most end users never run into that, even if they create their own content, is that most of the licenses are set up to not kick in until you produce over 100,000 copies of something. So actually, Adobe has something very similar. There's an Adobe. Let me fix this up here while I'm thinking about it. There's an Adobe. I think it's one of their fillable document formats that you are free to use until you created some number of thousand copies of the document, and then you have to start paying by the document. So codecs can be encumbered by a license agreement, and so either the browser manufacturer or the mobile phone manufacturer, the software, this company publishing software that allows you to edit or use software. They, depending on the use, they may have to pay royalties, pay license fees to the various license grantors, I suppose is the right word. So Google actually came up with some of their own codecs that are unencumbered.
Yep. WebP and WebM.
So let's see, as
VP9.
VP8 and VP9 and are codecs, and WebM is a container.
I'm glad you're getting that straight, because I don't remember. I could never remember that one.
Yeah, WebM is a container. VP8 and VP9 are video codecs. I think is it OGG? I think it's the audio codec that goes with that. But I can't.
OGG's been around for a lot longer than Chrome came up. OGG's the old one.
There are unencumbered audio codecs as well.
OGG is one of them.
Yeah, it's not. I didn't mean to imply that was a Google produced one.
That was my
it's used in conjunction with the Google ones, which are video specific, to create kind of a combination of audio codec, video codec container that you can actually use without running into licensing issues.
Yeah. Yep.
So while we talked about analog audio here, obviously the things like the Twitch stream you're watching right now, or the YouTube video you're watching, if you're watching this after the fact, is a combination of multiple codecs that contain audio and video in different formats, and so they get bundled into a container, right? So at this point, let me grab one of the tools that I found in the book, and it is an application. Now, the interesting thing is many of these applications are actually pretty old. So they have a look and feel of Windows 95, and oftentimes have been updated in a long time. One of them that I thought I was going to show, because it was a kind of a nice visualization of bitrate inside of a video file, is so old that it is no longer supported. It's no longer developed, and you can only find it on third-party sites. It is not signed by anybody, and I decided not to install it. I just didn't know if I was on the right site to,
Yeah, that seems awkward.
So let me start out. I do this off screen, or grab something from here in just a second. So give me a second. Whoops, that's not what I wanted. I want to go there. So I'm going to grab one of our YouTube videos and drag it in here. And I'm going to do a couple different things. I know this will make it somewhat better. I know this is not great yet. So I'm going to see if I can make this work. So I opened something called it's a date encoded thing. Basically, I opened an MP4 file, and so this tool shows me that this is an MPEG-4 formatted file. This is the MP4 MPEG-4 is the container. And it has some, it has obviously some information about the details. And then let me scroll down here. Then there is a video stream in here. So the video ID is 1. It's using AVC, which is H.264. I'm pretty sure. It's just an alternate name for H.264. So there's our codec information. All right, and then there's a whole bunch of information. There's a codec ID. And information. So this is AVC1 is the particular codec. And one of the things that I think is important that I want to talk about a little bit later on today, as we go, is there. Notice that there are a whole bunch of very specific settings. Very specific bits of information about the video stream. So codecs aren't monolithic. Codecs have let's see. I'm going to go to the tree view here. Yeah, this is going to be better for later. So codecs have let me do this again. So codecs have parameters. They're not monolithic. I can configure them. And part of the container format is designed to show me, let me see let me incorporate in the file the different settings. And so you see things like bit rate, maximum bit rate, aspect ratio, and the width and height of the video, frame rate, and so we're going to talk about those things. And then this file, of course, this is one of our YouTube videos, so it has video and it has audio. This is the AAC audio codec, which I think is Apple's, if I'm not mistaken.
I feel like because H.264 and presumably the matching audio codec. I know H.264 was an Apple.
Yeah, H.264 is an ISO standard, ISO/IEC standard, but I think it's based on something that Apple developed. And noticeably there's a lot less. There are a lot fewer parameters for audio than there are for video, but there's still a few. All right, so this is yes. What does this do? There you go. Go away. So this is our container, and within the container, that we sort of have the actual video and audio data, but it is encoded or stored in the file of the stream in a way that allows the receiver to properly pull it apart and display it to the user. Let me see. I think I've got there we go. This is an audio only file. This is an MP3 file. So this one, this is MPEG audio, which we know as there it is. So this is like a bit of background music for videos. And if I wanted to, I could actually play it on stream because it is specifically not royalty encumbered. That's why I bought it. So MP3 is MPEG audio. So it's a different container format that's meant for audio. And so it contains some information about the audio, specifically, things that you would see on Spotify and what have you. What's the album name, who's the artist, what's the genre, and that sort of thing. And then this is MPEG audio. Yeah, so I'm not entirely sure what the codec is here. It's the MPEG audio codec, but it has a different name that escapes me right now. And it is two-channel audio, so there's really two not two audio streams, but there's two coupled audio codes, and we'll talk about the sampling here in just a second. Okay. So by the way, this is a tool called Media Info. Very useful. Basically, it reads the container, and it displays reads the container and it displays what it sees in the container, which is super helpful. It's a really cool tool. I said it's kind of old. I don't think it's being. I think it is being supported because it certainly seems to have no trouble with any of the codecs or containers that they're currently in use. Although most of them have been in use for a while. Right. So the next thing I wanted to do is let's go here. Next thing I wanted to do is talk about audio, which is a lot simpler than video. So audio encoding is mostly a matter of so we're talking about audio now. And so this is mostly a matter of doing an analog to digital conversion. Right? And so we get audio from a microphone, from an instrument, like the pickup in a guitar or something like that. And we have to create a stream of numbers that represents that audio signal. There's really only a relatively small number of things you can do to make that happen, right? You have to basically take samples of the analog signal at a particular frequency, and then convert those samples to numbers using a particular number of bits generally. Right, and so I think rather than my trying to draw that here, let me go to another tool. Let's start here. So this is a tool called Audacity. Highly recommended. It's it's a really useful tool for recording audio or modifying audio. And so what I did here is I loaded up another one of these sort of 1-minute music clips from that music collection I bought. And if you don't look too closely, this is what an audio signal looks like. This is what you're seeing here are essentially the if you were to look at this on the wire that comes from my microphone running to the computer, this is the electrical signal you'd see. It's basically just a rapid oscillation of the electricity going back and forth, and it's a representation of the vibrations that my voice box makes and that the microphone picks up. What we can do is we can take an area here and enlarge it, and you see a bit more sort of the general you can see more of kind of the what you simply typically see in a textbook, right? So these waves, the squiggly lines that represent audio signals. So what is kind of unfair here is this is already digital, right? Because I'm just loaded an MP3 file, so which I know has already been encoded. This is actually a digital signal, but if I don't look too closely, it resembles the analog signal, and that's of course the whole point, right? This program, either if I were to play the audio or if I just look at it on the screen, basically converts those numbers back into something that looks very much like the original signal. That's obviously what we wanted. Now, if I keep going, if I keep zooming in here, there we go. And let's see, let's go to an area that's maybe a little more interesting. There we go. There. By the way, there are two signals because this is stereo. This is a stereo audio signal, so there's two channels. This is what when we talk about sampling, this is what we do. All right, so if I can zoom in a little bit more, each of these dots on the screen is a sample, and notice that they're kind of they're spaced out evenly. In effect, the decoder, the one is if I play this back, basically what the decoder does is connect the dots, right? So at a high level, converting analog audio to digital is not super difficult. You just have to basically at a particular rate sample the inbound signal. So the quality and the required bit rate all depends on two things: how often do you sample, and then how fine-grained do you make the values of the samples, because you have to represent them in a finite set of bits. Usually, so it's kind of, see, I've got to bring my magnifier back up here because Audacity actually will tell us. So Audacity tells us that in this case, what we're looking at is a signal that has been sampled 44,100 times per second, which is one of the standard frequencies. And each of the samples is encoded in a 32-bit number. Right, and so this is very typical for good quality, high quality music. Right. So one of the things that and you don't have a lot of freedom in audio codecs. This sample rate is not arbitrary. There's something called a Nyquist criterion, a Nyquist rule, that basically says that you have to, if once you choose a sample rate, in this case 44,000 hertz and change, the highest frequency you can properly represent is 1/2 of your sample frequency. All right, so when I sample at 44,000 hertz, what I'm really saying is I want to represent music or sound up to 22,000 hertz, which should be pretty good. Human hearing tops out around 16 to 18,000. Mine probably much lower than that because I'm old. In fact, as I
And
recall, there are some malls and stores that have taken to broadcasting. They installed speakers. They broadcast very high frequency tones because us old folks can't hear them, but the loitering high schoolers
yeah,
can hear the sound and tend to walk away, which is kind of weird.
yeah,
So
no, I can attest to this. I have a very strangely high top end of my hearing range. So, anecdotal. My wife, we have a next door neighbor's dog who has been barking quite a bit, and the internet tells you get a dog whistle and you train your neighbor's dog basically to stop barking.
mm.
The only problem is I can hear the dog whistle. So,
Ouch, that
as to the
hurts.
story, yes, I can attest that they put these high pitched things. There was an old grocery store I would walk by on my walk home from work that did it, and it was extraordinarily unpleasant to walk by. So
So,
yes, it does happen.
generally, most musical performances won't go up to over 20,000 hertz. The most instruments will produce can easily produce frequencies above even above the range represented here, but they will but generally most people, PX slip notwithstanding, can't actually hear that. So we generally don't try to account for him. Although the other common frequency used for audio encoding is 48,000, which would get us up to 24,000, which is, I think that's probably pretty much as high as they go. We can look because I can. Let's see.
You can create a new one, right?
If I try to export, I think it's going to. Does it use a preset? Bitrate, quality. No, that's not what I wanted. There is a way here somewhere where it keeps track of the. So even you can set it. I just don't remember. I just remember in the right offhand where in the tool that I can do that. But I think 48,000 is the highest that you typically use. So let me turn this back off. So let's go back to something a little more sensible. Well, I'll zoom in a little bit. There you go. So actually what I'm going to do here is I am going to select the entire audio.
Interrupt you really fast and say hello, old depressed gamer.
Oh, hi.
He's just joining us.
Odijit, thanks for joining us. Appreciate you dropping by. We are digging into codecs. Or well, not digging into. We're talking about the principles behind codecs. And just talking about audio, and we'll get to video here in just a little bit. We've got about a little over half an hour or so on our stream here. But hope you had a great stream. I know you were chasing aliens in Elite Dangerous. I hope it got a little bit. I hope your skill with the flak weapons got a little better. Those looked at tough boss fights. So what we're looking at here is this is our entire about roughly 1 minute long music file, and one of the things that Audacity will do very nicely is it will plot the actual frequency spectrum. And so I'm going to do this, and I'm just going to call it out here, and I think you can. Rather than trying to, so what this does, it takes the entirety of that 1 minute music performance and figures out what frequencies are in there. And this one, remember, we're sampling at 44,000, so technically I could see frequencies up to 22,000. The last little bit of signal here, that last peak at least, is where it's about 18,000 or so. And it's kind of hard to see. Let me turn my magnifier back on. It's right down here, except except I can't both hover over and magnify this. So there's a place where you can see the actual the actual value at the cursor. So you can have to sort of trust me them reading it out correctly. I encourage. It's fun to play with. It really is. And it's free. Audacity is free and available for all the major platforms. So it's really super easy to get. So this is about. So the last peak here, and this is already quite. I mean, this is a logarithmic scale, so we're going from effectively normal, just more or less at full full volume up here. We're see, every 6 dB down is 1/2 signal power. So this peak here is 50 dB down, so it's there, but it contributes not a whole lot. Fortunately, because that's a really screechy, loud, high frequency. But right above here, this is like so these are both. This is a logarithmic. So the typical notes you would normally hear, the bases of the notes, not the harmonics, would be kind of this range, a few hundred hertz to a few thousand hertz for the higher octaves, and then most of this represents kind of overtones, harmonics, and those sorts of things. All right, so this is pretty cool. Yeah, so one of the things we have to decide after that determines the what we do with a codec is essentially based on how many frequency are we trying to capture, right? And one of the things that started all of this was telephony. When the telephone networks first went digital, Bell Labs in the U.S. somewhat arbitrarily, well, not entirely, they did some focus groups, but they ultimately settled on 4,000 hertz as the top. So the original telephony codecs all run at 8,000 samples. So I think I've got a couple of let's see. Yeah, I'll take a look at this guy here. It's kind of interesting. So these are some sample files I picked up. Now let me get this one. I'm gonna have to scroll through here, I think, otherwise it doesn't make a lot of sense. So this is a file that starts out with like a very low tone, like I think it's like 500 hertz, which is sort of a near the middle C kind of thing, and then it ramps up to you can see it gets higher and higher and higher frequency. I think it goes to 8,000 hertz, and then comes back down. And so if we take the there we go. All right, so yeah, of course, if I look at the entire file, and I can't remember how long this is, it looks like it's about 8 seconds long. So you can't, if I'm zoomed out all the way, you can't really tell that I'm going from a low frequency to a high frequency and back. This was done at 48,000 hertz, so they basically threw the best codec possible at it. And if I do, if I look at the spectrum for this guy, make this bigger. If I look at the spectrum for this guy, it tops out at almost exactly 8,000 hertz and has some very, very low volume noise and up in the top. So basically, because it ramps all the way up and back down, overall, over the entire signal, I'm seeing something that basically starts at very low frequencies. Looks like it. This is about 100 hertz or so when gets up to basically full volume and then goes all the way across. And I could zoom in a little bit here. Whoops, and just grab basically some of the early part of the signal to maybe to about there, and we'll get the spectrum, and this is basically ramping up to about 700 hertz or so. All right. So what they did, and what was kind of interesting, the last file I want to show here is this is that same file. Whoops, where are you? There. This is the same file, but in nope, it is not. There. I will find it eventually. There. This is the same file encoded with an 8,000 hertz codec, basically a telephony codec. And remember that, grab this here and stretch it out a bit. And we'll kind of go maybe here, stretch that out a bit. All right, so what was going on here is I was ramping up, we're ramping up the frequency, and right about here, when we get to probably close to 4,000 hertz or so, the codec can't handle it. It has to filter that out. Right, and so at this point, by the way, if you don't filter out, this actually the same site has another file that shows how to do it wrong, and you get all sorts of noise. But if you use the codec properly, it just can't reproduce a higher frequency. And so if I go back to the entire file here and do a spectrum analysis of this, the top here tops out at just 3,800 hertz, basically just and that's because of the filter that has to prevent the higher frequencies from getting in. It actually cuts out earlier than the 4,000 maximum. So this one basically cuts off. You can see this that drop off starts at about 3,000 hertz or so, and that is correct for what we used to do in telephony. So I'm going to send these back down. All right, and so for example, so a telephony codec would my tablet bit going here. So telephony codec would use 8,000 samples, and the telephony codec uses 8 bits. So you end up with a stream that is 64 kilobits per second, and it's constant. And the music stream we just looked at, and I'm going to have to pull out my calculator for that one. Remember, that one was 44,000, was it 100?
Yeah.
44,100. And we're using 32 bits. So let me pull up my calculator here. So we're going to do 44,100 times 32 bits. So that's 1.5 megabits per second. All right, so for audio, Uh, yes, ODG says there's a YouTube guy who makes music through an oscilloscope to produce pictures. Um, kind of high-tech ASMR, right? Yeah, you can do all sorts of crazy stuff. So in audio codecs, we don't have a lot of options. Now, what you can do is use compression there, and so different codecs, especially for high quality, use various compression techniques, which they get very mathematical very quickly. Some of them are based on how, especially the ones that are designed for telephony, like the ones in our cell phones, at least the second and third generation cell phones, we're trying to use very low bit rate codecs, much lower than the 64 kilobits per second even. And so they took advantage of kind of knowing how your voice box produces sounds and syllables, and so they're using compression by basically recognizing that that was part of a T sound or part of an O sound, and instead of transmitting it, transmitting a much shorter a much shorter code that says reproduce an O sound, in effect. So the so somewhere in between the 64 kilobit per second telephony codec, which definitely is not, it's perfectly good for conversations, but you wouldn't want to listen to music over it, as we looked at the spectrum for our music sample. And of course, the one here at the bottom, the 44 kilohertz by 32 bits, that's really good music reproduction in an MP3 file. And if you're streaming that, it'll probably be compressed in some form, but to make it less than 1.5 megabits per second. So not terribly many choices, but so if you play around with Audacity and take a file and then kind of resave it with different settings, and different codecs will have different options, and the different options will kick in different compression schemes. There is not much. The nature of audio sampling is such that all the books I looked at suggest that there's not, contrary to say like JPEG images, like an image file, there isn't very much you can compress out of an audio file with the sort of typical, like throwing the zip at it or something doesn't do very much. You generally have to do lossy compression, where you basically give up some of the quality in exchange for lowering the bit rate. And so and again, this is not meant. We're talking about. We're going to talk about all of this for like an hour and a half here. This is not meant to dig terribly deep into codecs. Although if I learn more about it, I might do that in one of the streams. It's really more. Really, what I was curious about is, what are the knobs, and when I turn them, what happens, right? And so you really the sample. The sampling frequency is sacred. I mean, if you lower it, as you saw in that comparison of the 16,000, or basically the high quality encoding of the 8,000 hertz sound, and then we go down to an 8,000 sample, and basically everything above 4,000 disappears. If you try to change the sample rate, you are going to dramatically impact the quality of the audio. But there are other techniques you can use. Certainly, you can drop the number of bits down. I think game audio tends to be 16-bit audio, I think. Don't hold me to that, but it's I think game audio, because again you have so much of it, and it has to be dealt with really quickly.
Imagine there's a bit of a mix.
It depends on cutscenes versus other things.
In-game like dialogue audio, some of the music.
Yeah.
Those pieces are probably higher.
Yeah. Basically, you can encode each one differently, and I think that's, from what I've read. I just got an excerpt from a book that that same colleague sent me. I haven't had a chance to really read through it carefully, but it sounded like they're essentially sort of different quality points. In fact, the book I mentioned earlier, for audio video streams, talks a lot about sort of matching the quality settings to the audience, to the content, and so on. All right, so let's take a little bit of a look. I don't have anywhere near as many things I can demo here, but let's take a little bit of a look at what happens in video, because video is really different from what we just looked at. So first of all, sort of trivially, a video. First of all, video is generally not a matter of doing analog to digital conversion. Let me get this guy out of the way a little bit here. Video is not generally it's not generally a matter of. I think I want this again later, so I'm gonna move it somewhere else. Let me just minimize it. Because the cameras we work with, like whether a webcam or professional, broadcast cameras, whatever, those all generate digital. Ever since we went away from film, pretty much they're all digital. So
Making a comeback.
What's that?
I'm just laughing at the recent trend where physical, old school chemical film is coming back.
Yeah, but probably not for web streaming.
No, not so much. This was one of those moments.
Right. No, I understand. So when we encode, so video is more a matter of encoding it, and so let's take a quick look. So video is essentially a series of pictures. Typically, anywhere depending on the standard, depending on the convention. Generally these things are referred to as frames, and we're generally running something like 25 to 30 frames per second. 25, I think, is it's actually borrowed from the old film. I think the old film cameras, projectors ran at 24, 25, and most video on the web is 30 frames per second, which is the low end monitors can all run at least 30, and obviously many can run 60. So if we don't do anything else, obviously we know that because this is already a digital image, right? So this is actually each of these frames is are various rows of pixels with a certain number of columns. I'm not going to draw all of them. And so like a 1080 monitor or video stream would have 1920 pixels across by 1080, hence the name of pixels down the shorter side, generally the vertical side. Each of these pixels is a color dot. And this is actually something I had to go and look up because ODG said my most high-end audio systems are still analog, from what I understand. And then before you dropped in, we were talking about the fact that like my headset is analog. I think PX Lab's headset is an analog as well. So yes, audio is different. Audio, both input and output. Actually, output has to be analog, because that's what we do in a speaker. Basically, has to move air, create pressure in the air, because you try to couple into the ear, how our ears hear. So audio always involves an A to D and D to A conversion, analog to digital analog. But nowadays, at least, video does not. All right, so I have a matrix of pixels, and again, just sort of naively, if I don't do anything else, each of these dots. Let's see what do I want to do here. We'll use this guy. So this guy here, if I break that out, what we think of as a single pixel is really a what do you really has to represent a color. So generally, I need I need three different colors to mix the set of colors I want, and a monitor will use red, green, and blue RGB emitters, and so each pixel actually has to be told three different values: a red, a green, and a blue, and then it mixes together the color. So one of the things that I had a little bit of trouble tracking down, finally, I think, I'm pretty sure that in like my digital my digital camera I use, the camera can produce it can use up to 24 bits per pixel. Well, no, they can use up to at least 16, maybe 24 per pixel. The format I normally work in when I work on images is 16 bits per color per pixel. And JPEGs are 8 bits per color per pixel. And as far as I can tell, except with the exception of things like high dynamic range video and some other really high-end video formats, for which there are very few monitors, most of the video we work with is 8-bit per color per pixel. So technically it's 8 times 3 bits. So if we do that math, things will get scary really quick. So let me grab my calculator again. All right, so we are. Let me go here. So we are looking at 1920 pixels across times 1080 pixels down. So this is, by the way, this is the if a camera like in a phone or a digital camera says the camera is a X number of megapixel camera. So a 1080 monitor is a 2 megapixel monitor. So you have a little over 2 million pixels. So now I'm going to code each of these pixels with 3 8-bit numbers. So I need to do times 3 times 8. Is that right? Times 3 times 8, yes. And I'm going to send 30 frames per second. Which is for games, that's not a very good frame rate, but for most, that's what we use for most video. So times 30. That is make sure you count the numbers. That is 1.5 gigabits per second, which is not a fun number if you're doing networking. All right, so video codecs are all about compression. As they already start out digital, I could technically grab this stuff and just ship it. But at 1.5 gigabits per second, that really isn't terribly feasible. Right?
Well, and that doesn't even take into account what happens if you want to do proper 4K video.
Oh yeah, no, I mean that's a 1080, right? So and 4K would be what, 16 times as much, right? This is 4.
Sounds right. Yeah,
it's four
times.
Each side. This 1080 is 1/4 of a it's 1/4 of a 4K monitor.
Yeah.
And so you end up with 4 in. What's it? It's just a quarter. No, it's an eighth.
Yeah, I would say it would turn into it would, wouldn't it?
Yeah, is it? Was it
or
for?
are we even?
Well, it
Either
will
way, doesn't matter.
it will
By a
multiply really
significant number.
quick,
Yes.
really quick. So video codecs. First of all, there are a lot more of them. Because they can all use, there are various different ways of doing this. So just a couple of notes on how that might be done. All right. So the first thing is there's a chroma sampling that goes on. So the instead of and this is something that I have not dug all the way into yet. But there is and you'll see it when I bring up the media viewer again here in a second. The um, uh, the encoding of the color information is done in like 2 rows of 4 pixels each, and you basically sample only a subset of them. So that you get a little bit of a savings from that, and it's something that you can configure into the codec as to how careful you want to do that. Then most codecs will do I'm going to draw it in here. Most codecs will look at 16 by 16 pixel blocks, and then do all sorts of try to do all sorts of local compression, frame-to-frame compression. It's one of the things that I know ODG on his stream and I looked at one point. Is there are so-called iframes. In most codecs have a concept called iframes or keyframes. So every now and then you actually send this full picture, but most of the time you analyze the picture in 16 by 16 blocks and decide which blocks have actually changed enough to send in the first place. And some codecs are smart enough to realize that this block, if there's some movement, like the camera's panning or what have you, some codecs are smart enough to say, yeah, don't worry about it. Just take this block and move it by a certain number of pixels. But I'm not going to tell you all the values again because they haven't changed. You just need to move this thing over. Right? So the sophistication of different codecs, different video codecs, comes from all of the algorithms built into this sort of compression. How many iframes do you send before, how many keyframes do you send, or how many frames do you send before you send another keyframe? And how aggressive are you at doing this sort of compression, right? And this is where the bit rate comes in, right? So you generally don't set specific parameters around the compression. You set a target bit rate, and the compression will get more and more aggressive to meet your target bit rate. So that's where that's the external knob. Aside from frame rate, and you could certainly drop the frame rate down if you needed a video that can run on a slower connection. You could change the resolution, and those of you on Twitch can actually do that. Manually. There's a little gearbox in the bottom right, I think it is, of the video screen, of the video player in Twitch. You click that, you can normally the playback is set to auto, but if you click on that, it'll actually offer you like 4 or 5 different resolutions, all the way down to something really silly like something that's like 300 pixels wide, for really bad connections where you have to drop the size down, right? So you can certainly change these numbers. Yes, ODG is saying that the codecs have, part of what the codecs do is have some, they've built into them are some very interesting ways of using essentially optical illusions to fool the eye into seeing more than is really there. So you can change the resolution, you can change the bit rate to try to drop your bit rate, and you can of course get more aggressive about the various actual image compression. And this is lossy compression, right? So you lose information. My favorite example is, and it's a great movie anyway. But I was watching the movie Twister. Lots of tornado stuff going on. I was watching that over a on my. Back then it wasn't called Hughes at the time. It was called DirecTV, I think. I was watching it on my satellite direct-to-home link, which was capped at, it was a hard 1.5 megabit per second limit. And in that movie, there's a scene where you're basically inside a tornado, and there are cows and houses and all sorts of stuff flying around in circles. You could see the compression artifacts. There were basically blocks like these. They were stationary. So so the stuff was flying around. All of a sudden, there was kind of a block of pixels that just didn't change. So it's still, part of the cow just got stuck for just a few frames. It was very visible because at some point they just had to give up and say, prioritize and send the really important stuff, but some stuff can't make it. Yes, Odie says he loves that film too. Macro blocking can be very obvious in this film, which is what this is called, where when the codec basically works on blocks of data in the image. Right. So just to get kind of a sense of what that looks like, I'm going to drop back into this my media viewer here. And I'm going to grab myself a video file again. There we go. Grab that YouTube video file again. And this time we're going to kind of focus on the video parameters. And let me bring this guy up. All right, so our video codec, which is essentially it's AVC, which is the H.264, and some of these I don't know what some of the stuff I couldn't tell you what it is, like the reference frames. I have to look that up. So apparently, when I really need to look at it now, because I was using a video editor, and the target bit rate in this particular file is 500 kilobits per second. The maximum bit rate is 11 megabits per second, which is a lot higher than I thought it would be. So one of the things that the books on streaming talk about, including the book I showed earlier, is that and again, if I was braver to install that old tool, I could show it, but I'm not that brave. I'd install an unsigned file on my Windows machine. The output from a codec is not constant bit rate typically. So depending on what goes on screen, and this is why that movie started blocking during that scene, because there was just too much going on. The bit rate went up and up, and it went above the channel bit rate. So you can sort of see that here, and I must have really waved my arms in amazing ways to generate that. I have no idea. I really want to find out now where that is. So I need to see if I can find another tool that isn't as scary to install to actually get a view of that. The problem is a lot of these tools, a lot of the authors have migrated to producing commercial software, and so this tool, this media viewer tool, is free. and some of the other ones are as well. And then in that same book, he says, "And here's another tool that's really good, and it's about it's about $2,000 per seat, license fee." I'm going, okay, yeah, I'm not going to rush out and buy that one. So this is one of the early files I was doing. I think 720 is not 1080, so it's a little bit smaller. The target frame rate is 30, but it will vary a little bit again. I think because of the keyframe. I had to look up the the color space. Because I didn't know what it was, and none of it makes sense. I haven't looked at the definition of YUV encoding, but what I found out is it goes back to television, which is where a lot of this stuff started. So we talked about, and you can sort of see it over in the right next to the block that I have highlighted. So on a monitor, each pixel is an RGB triplet, a red, green, and blue dot. But in the early days of color television, the signal sent by the TV broadcasters was supposed to be easily used by both the old black and white television sets and the modern, we're talking about 1940s, 1950s, I guess 1950s, depending on where you were, the black and white television sets and the color television sets. And so instead of sending an RGB triplet, basically the first thing the codec does after it does everything else, the first thing codec does is it computes a black and white conversion. If you've ever done image editing, still image editing, in like Photoshop or Lightroom or one of those, if you convert an image to black and white, you basically select how much red, green, and blue you want to include, and the white, gray, black range gets mixed together based on converting red, green, and blue to just basically a grayscale. So the Y value is the correct black and white value, and then U and V are needed to recalculate what the RGB values were in the first place. So the idea was that when you send out this combined TV signal, a black and white set just read the Y data, ignored U and V, and displayed the black and white image. And if you had a color set, it would then take U and V and do the calculation and get the RGB values back. And so I guess that is still being done. And the chroma subsampling is that what I was talking about earlier. And again, I need to get a little bit better at understanding what they mean by what all options are. But chroma subsampling of 420 means that if you take 2 rows of pixels, 4 pixels wide, so 8 pixels altogether, in a 420 subsampling, you sample 2 pixels from the top row and ignore the second row in that block altogether. And if you think so if you want a better color representation, then you would go to the other common one is 422, and of course by reducing the number of actual data points you're sending for a group of pixels, you cut down the data rate. the bit depth is actually encoded here. So the YUV, which are really the RGB numbers, are transmitted as 8-bit 8-bit numbers. The only other thing where I think we're going to conclude today. So I had to kind of work on this, understand this a little bit. It was kind of a kind of obscure concept, and it doesn't help that the labeling is it gets confusing. So there's a value here, right where I'm running my cursor across, that is labeled bits per pixel frame. And what they're really talking about is, if you're looking at if you're calculating the number of pixels per second that you're sending in the stream, which is obviously the size of the image times the number of frames per second. If you divide that into the bit rate of the stream, you get basically you get a measure of how much compression you're doing, right? So in my 1080 so 1920 by 1080 monitor picture, and at, let's say, 30 frames per second, there's really nothing, the number of pixels per second I'm sending is fixed, right? So the lower the bit rate, the higher the compression has to be. And so for this particular video, the compression is 0.018. So I'm using not quite 2/100th of a pixel of a bit for each pixel nominally. Of course, that's not how to encode it. The fact that we're using 8 bits per pixel to represent colors makes this really, really confusing. Which is why they use this bits per pixel frame. And I actually did some digging around through bulletin boards, and people have said, well, I'm going to get rid of that nomenclature altogether and call it the compression ratio, which probably makes more sense. But this has nothing to do with how the bit depth, which is a couple lines above this. This is a measure of the quality of the quality of the stream relative to the resolution and the frame rate we're sending. So apparently, the 0.018 I think is fairly typical. There are I think the highest value that I think I saw. I've seen some, and again, this is something we're going to maybe get into a little bit more next week. So you can look at different. I've seen a couple of places where people analyze this bit per, basically this compression ratio for different type of online streaming services, Netflix, CNN, ESPN. Not surprisingly, ESPN has the highest bits per pixel frame number, the lowest compression. Makes sense, right? Because in most sports programs, things move around really quickly. Whereas, if you have a talking head like me, you really don't need anywhere near the same fidelity, right? You can get away with a lot more compression. So ultimately, this is actually one of the key aspects of understanding when we set our in our like OBS broadcasting software or in any other, like video editors, and I'm going to start looking at these things much more. When we do that, we're implicitly, by setting the bit rate and by making other choices, we're setting this compression ratio, right? And we're basically we end up with a particular compression ratio, bits per pixel frame ratio. And there are actually some best practices that say, did you make a good choice? Are you sending way more stuff than you should? Or are you sending so little that the quality will suffer and you get a poor video, even though it nominally has the right, is 1080 and the right frame rate? It's not going to look very good because you made this compression too aggressive, right? Like the cow that didn't show up properly in the tornado. So I found this really fascinating. ODG has said they never looked into the side of things before. I hadn't either. This is why I thought it was so interesting, because you really don't have to get terribly deep into this whole block coding of that the codecs do, but I'm perfectly happy to think of my codec as a black box. Right? We kind of talked about black box debugging. I mean, I'm perfectly happy to do black box encoding, as long as you understand that it's like a black box with like 3 or 4 knobs on the outside, and I really need to understand what those knobs do. And this particular number, this particular concept, I think is one of the things I took away from it. That's this is a way of determining what's sort of the target quality of the video. And I would turn around from a networking perspective, if we know we have to support a certain type of service, like the ESPN, obviously you're going to have to send higher bit rate data because you need a lower compression ratio to produce good video for your users. So this is one of the places where this is one of the key numbers that you can use to say, I made a whole bunch. I set these knobs in certain ways. Did I actually create something that makes sense? So I found that really, really cool. The other piece, and again, one that I want to take a look and see if I can, find a non-scary to install tool to look at it with. But the fact that the bit rate changes throughout the course of the file has implications, right? Especially for real-time video, where we do video conferences like Teams or Zoom conferences, where you really want all the data to flow through the network without getting delayed because you're shoving so much data at it that things get queued up somewhere. So if this analysis is right, and this file actually has, actually places where this file suddenly plays at 11 megabits per second, I want to know what on earth I did to cause my file to need that level of bit rate. Right. I think that's kind of covers what I wanted to get through today. It was sort of fascinating to dig into this, not from the math of how you actually create a codec, which I don't understand how to do, and not just from like a raw bit rate, but just I never really had a good sense of the interplay between. I had some understanding of it for audio, but I never really had a good understanding. I don't have a good understanding now, but I have a better understanding than I had before. ODG says, turn the lights on and off so all the pixels change, and yeah, that's maybe what it was. It was just like a scene change or something that caused it to have to do something dramatic. But the video encoding for transmission and streaming, as I said, is a lot more complex, but it's but I think this sort of level of understanding is what I felt I need to make reasonably good choices about how to set up a broadcast, for example, or a stream. And I'm going to look at my OBS settings now and say what am I doing? What are my settings in OBS, and are they reasonable? Same thing for YouTube. But then it also, of course, gives us more of a sense of, if we're providing network services to support video conferencing or streaming, what are we dealing with, right? And depending on the number of streams and this compression ratio we expect, we can at least get sort of a sense of what we have to support on a network.
Well, and it's an interesting conversation to have about some of the protocols that are used for live streaming, HLS and Dash.
Right. Yep.
Sort of looking at the ways that they handle adaptive bit rate
Yes.
for the client.
Yes. Because so in the discussion here, I sort of said I can sort of said I can change the size of the frame or the frame rate. Of course, that can happen automatically in an adaptive bitrate transmission. Let's see. ODG says I was more on the MPEG-3 transport stream rather than the MPEG codec, right? I do wonder what Twitch now uses, as OBS can send separate audio for I think the separate audio for VODs, which is big, is OBS already has 6 audio streams, and so it'd really be kind of fun to look and see what's actually in the stream, but. The container format certainly supports multiple audio streams. It's just a question of, I think Twitch has now decided that they're going to block, I think, one of the streams, or only run one of the audio streams to VODs and that sort of thing. MPEG 2, right? So I think for me, some of the next things I want to do, first of all, is to kind of play around with some of the video editors. One of the tools, I actually ordered a book because I really want to get better at it. There's a cross-platform tool called FFmpeg, which is a command line tool. I have it on my Linux machine. I haven't installed it on Windows yet. It is the Swiss Army knife of video transcoding. But you really have to know what you're doing, and so I actually ordered a book on FFmpeg concepts, because, as with many other open source software, the documentation is, shall we say, a little dense. I also ran into, just as a total sidebar, since PX Flip and I had the conversation about open source a while back. So I ran into a weird problem. As I said, I have FFmpeg installed on my Linux machine, just standard, apt install kind of thing. I run FFmpeg and I get like a half a screen error message, codec versus library mismatch. I'm going, what the heck is that? It seemed to be doing everything fine. So I started digging through the usual Google bulletin boards kinds of things. And I kept finding this same error message going back 10 years. And basically, ODG says OBS uses FFmpeg, I believe. Yes, I think it is. Great tool, but so many options that makes it unusable without Google search. Well, that's why I bought the book. So I want to learn how to use it.
Let's face it, the minute anything touches either audio, video, or image standards, FFmpeg comes out. Literally, earlier today in my day job, I was looking at image source sets for better performance for a website.
Yeah.
And lo and behold, FFmpeg popped up.
Yep. So I Google this error, and basically there were at some point somebody said this started like in Ubuntu 14 or 12 or something, and every now and then somebody figures out if you uninstall this particular codec library and force app to install a different one, then the error will go away. So I now came to one entry that, and I looked into that, and that doesn't work anymore. And I'm running basically the equivalent of what an Ubuntu world is 20. I'm running a Debian distribution that is equivalent to Ubuntu 20. I couldn't find anything that would actually do that properly without uninstalling, but about half the software I have on the machine. But somebody said, why we get this error message? I mean, everything's working. It just, the libraries have different names, I think is what the problem is. Because the funny thing is the error message lists the version mismatches that it's complaining about. And in every place where somebody posted the error messages, the two columns of versions are identical. It's just somewhere behind the scenes, the library names are different. And so somebody asked the FFmpeg people, can't you just finally fix this? And they said, that's not our problem. We just write source code. How somebody compiles this is not our problem. Yeah, thanks, guys. It says also it's one of the open source projects that refuses to build binaries. So to install this on Linux, you get it through the RPM or Debian packaging, official packaging distribution channels. On Windows, you have to rely on Joe Schmo's aluminum siding, and I also compile FFmpeg occasionally website. It's just fascinating. But yeah, so sometimes open source can bite you in the what. ODG says you can even do overlay stuff with FFmpeg. Yeah, problem comes from copy protected codec stuff. Yeah. So you can't always install the codec with the software. In this case, it really is just a mismatch of not of the codecs, but of the name of the library file that I think trips it up. But we talked about that a little bit earlier. I think before you dropped in that some of the codecs you can't just install from an open source repository because depending on your use, you may or may not have to pay a license fee. Yep, and there so some of there are codecs and I think it's something I guess it's something that we're going to chat about maybe in a future stream is some of some of the newer codecs like the ones the VPA VP9 from Google, which are essentially meant to replace or be parallel to, I think it's H.264 is normal video, H.265 is the 4K video. And then VP8 and VP9 parallel the two. Yeah. So they're so as ODG says they're essentially basically third party, in this case Google being the third party replacements for the encumbered H.264 and H.265 codecs. So bring this back around. So we're because as ODG and PX Lip and I, we're trying to set our streams up. We're trying to make the streams look good. We try to record our YouTube videos, make the YouTube videos look good. But then also basically as an IT teacher, my students go out and they have to support a 5,000 employee Fortune 500 company that suddenly does everything over Teams. Understanding these knobs and understanding how to do how to set things up, and I do not know about Teams. I'm already disliking Teams with a vengeance, so I do have to use it for teaching now. But in a lot of cases, I know with WebEx because I got into that a little bit. It's the end user usually can't touch these things, but as a system admin, a lot of times you can turn these knobs in the central settings, obviously, you can actually make these adjustments, but they're generally not exposed to the end user. It's usually exposed to the site or system administrator. So understanding how this works is super important to have a sense of what can if I turn this knob, what happens, right? And ODG, I was saying earlier, basically what got me interested in tracking this down is the time we spent on Ustream trying to figure out what happened when we with OBS Ninja when we set bit rates to different numbers, and it was sort of counterintuitive what it was doing. And I'm not saying I understand it now, but at least I think more tools to go back and say, what do they mean to do? Then maybe we'll enlist PX Slip to help us dig through the code and figure out what they're actually doing. Because I'm really curious in some ways of what's actually happening there. Because again, it wouldn't surprise me if they're using FFmpeg as well. So it's just a matter of finding out where they're calling FFmpeg and with what parameters would not be at all surprising. All right, I think we're anything from your end before we wrap up? Because I think it's we're actually kind of well beyond our normal time.
So we pushed a little late tonight.
Yeah, we did.
I don't think there's anything I really can add other than the comment I made. It's funny when things overlap. I was literally working on some of this stuff earlier today for my day job, looking at different codecs and containers for figuring out how to improve performance of websites I build.
Yeah. So yeah, that is. Yeah. I mean, what I found is there aren't very many tools out there. I mean, it's FFmpeg is it at the low level, and then there, some of the tools like the media viewer everybody talks about. So there's
everything else is just wrapper around it, just to make it using it easier.
And then there are dedicated software packages for really broadcast purposes that, but then they immediately shoot up to, thousands of dollars of licensing fees per seat. I mean, that's super specialized. ODG says there's a video on Discord you might enjoy. Now I was wondering about why 30 FPS is actually 29.97, how it came about. I will absolutely look at there's a lot of analog TV that is still feeding into all of this stuff, isn't it? Much like the 64 kilobit per second voice codecs. There's a lot of analog world that still sort of lingers in some of the settings. I will definitely look at that. That's I was wondering about that. That's fascinating. I'll definitely look that up. All right, I think we're going to wrap it up here. Again, either on Twitch, ODG, have a good night. I know it's very late where you are, so hopefully you'll get some sleep. So we'll say goodbye to folks here on Twitch, and if you've watched on YouTube. Then again, thanks for checking out this VOD, and yes, on Twitch you follow, on YouTube you subscribe. Please do either one of those or both. We much appreciate it. And with that, we will see you next week.
See you next week.
Bye now.